Right now, as you sit here watching this, Venus is spinning. But here's what will disturb you. It's spinning the wrong way. While Earth rotates from west to east, making our sun appear to rise in the east, Venus rotates from east to west. On Venus, if you could survive the crushing atmosphere and hellish temperatures, you would watch the sun rise in the west and set in the east. For over 400 years, astronomers have stared at this backwards world through their telescopes, measuring its rotation with increasing precision and asking the same haunting question: why does Venus spin in the opposite direction from almost everything else in our solar system? We thought planetary rotation was simple. Everything should spin the same way they formed from the original disk of material around our young sun. We were completely wrong. The reality is so much stranger than we imagined. Venus isn't just spinning backwards. It's spinning incredibly slowly, taking 243 Earth days to complete one rotation. That means a day on Venus is actually longer than a Venus year, which takes only 225 Earth days. This is a world that has defied every prediction, shattered every assumption, and forced us to completely rethink how planets can evolve. But here's what makes this deeply unsettling. Venus used to be like Earth. The evidence is overwhelming. This backward spinning hellscape was once a blue world with oceans, possibly harboring life for billions of years. Something catastrophic happened to our sister planet. Something so violent it literally flipped it upside down and transformed it into the nightmare world we observe today. Tonight, we're going to discover what force could be powerful enough to reverse the rotation of an entire planet. We'll explore the evidence hidden in Venus's current motion, uncover the traces of ancient catastrophes written in the geology of our solar system, and follow the investigation that has led scientists to three shocking possibilities, each one more disturbing than the last. This isn't just about Venus. This is about understanding the violent forces that shape planetary evolution, forces that could strike any world, including our own. Because if it happened to Venus, Earth's twin, it could happen to Earth. The story begins 4.6 billion years ago, in the spinning disk of dust and gas that would become our solar system. Every planet, every moon, every piece of debris was born from this disk, and they all began spinning in the same direction, the direction the disk itself was rotating. This fundamental law of planetary formation should have made retrograde rotation impossible. Venus shouldn't exist. Yet here it is, defying physics, spinning backwards at a crawling pace that suggests something went catastrophically wrong. The clues to this cosmic crime scene are scattered across our solar system. They're written in the tilts of other planets, the scars on ancient surfaces, and the chemical signatures locked in meteorites that have traveled across space to reach us. Dr. Alexander Correa from the University of Aveiro has spent decades studying Venus's rotation, and his research has revealed something extraordinary. Venus's current spin state is so unusual that it requires an explanation involving either massive collisions, gravitational resonances, or atmospheric effects we're only beginning to understand. This planet is telling us that the early solar system was far more chaotic than we ever imagined. The Magellan spacecraft spent 4 years mapping Venus with radar, piercing through its thick atmosphere to reveal a surface that tells the story of planetary catastrophe. The Soviet Venera missions landed on this hellish world and transmitted back images before succumbing to the crushing pressure and acid rain. Every piece of data from these missions points to the same conclusion. Venus is not behaving like a normal planet. What we've discovered challenges everything we thought we knew about planetary formation and evolution. We found evidence for collisions so massive they could flip a planet's rotation, tidal forces so powerful they could lock a world into impossible spin states, and atmospheric dynamics so extreme they could fundamentally alter how a planet rotates. But perhaps the most profound revelation is this: Venus's backwards rotation might not be a cosmic accident. It might be the inevitable result of processes that operate throughout the universe, processes that could transform any Earth-like world into a backward-spinning hellscape. Over the next hour, we'll journey through the evidence step by step. We'll discover why the traditional explanations fall apart when confronted with new data. We'll explore the cutting-edge theories that could explain this mystery. And we'll confront the unsettling possibility that Venus's fate could await any planet, including our own. If you're fascinated by planetary mysteries that challenge our understanding of the cosmos, subscribe and hit thumbs up. And here is a question that might blow your mind. What would happen to life on Earth if our planet suddenly started spinning backwards? Comment below. I'll pin the most creative answer. The journey into this mystery will take us from the birth of planets to the death of worlds. From gentle tidal forces to cosmic collisions that dwarf anything in human experience. We all discover that Venus isn't just spinning backwards. It is showing us that the universe is far more violent and unpredictable than we ever dared imagine. Now let's begin by understanding exactly what normal planetary rotation looks like and why Venus's behavior is so deeply disturbing to everything we thought we knew about how planets should spin. Chapter 1. Cosmic Pattern. To understand why Venus's backwards rotation is so profoundly disturbing, we need to first grasp the cosmic pattern that governs how everything in our solar system should spin. This pattern began 4.6 billion years ago in the vast molecular cloud that would collapse to form our sun and planets. Picture a slowly rotating cloud of gas and dust, hundreds of times larger than our current solar system. As gravity pulled this material inward, a fundamental law of physics took over: conservation of angular momentum. Just like a figure skater spinning faster when they pull their arms inward, the collapsing cloud began to rotate more rapidly as it contracted. This rotation created a flattened disk around the forming sun, with all the material moving in the same direction. This is the protoplanetary disk from which all planets, moons, and asteroids would eventually form. The direction of this original rotation became imprinted on everything that formed within it, creating what astronomers call the prograde direction. Dr. Alan Boss from the Carnegie Institution for Science explains it this way: the formation of our solar system from a rotating disk means that all the planets should orbit the sun in the same direction, and they should all rotate on their axes in that same direction. This is one of the most fundamental predictions of planetary formation theory, and for the most part, this pattern holds beautifully. Mercury, Earth, Mars, Jupiter, Saturn, and Neptune all rotate in the prograde direction, the same direction they orbit the sun. Even Uranus, despite being tilted on its side, technically rotates in the prograde direction relative to its orbital plane. But Venus shatters this cosmic harmony. Not only does it rotate in the retrograde direction, opposite to its orbital motion, but it does so at an almost impossibly slow rate. While Earth completes one rotation in 24 hours, Venus takes 243 Earth days, longer than its own 225-day year around the sun. To put this in perspective, imagine you're walking around a circular track while spinning. If you're like every other planet, you're spinning in the same direction you're walking. But Venus is walking forward while spinning backwards, and spinning so slowly that it doesn't even complete one full spin before finishing an entire lap around the track. This creates one of the most bizarre phenomena in our solar system. The sun rises in the west on Venus. From the surface of this backwards world, you would watch our star appear on the western horizon, crawl across the sky for months, and finally set in the east. The interval between one sunrise and the next, a solar day on Venus, takes 117 Earth days. The Magellan mission, launched in 1989, used radar to map Venus's surface through its thick atmosphere. The detailed rotation measurements revealed just how precise this backwards motion is. Venus's rotational period is exactly 243.025 Earth days, a number so specific it suggests this isn't random chaos, but the result of some systematic process. But here's what makes this even more mystifying. Computer simulations of planetary formation consistently show that all planets should end up rotating in the prograde direction. The gravitational interactions during the accretion process, the angular momentum of the original disk material, and the subsequent evolution of the planetary system all favor prograde rotation. Dr. Jacques Lasker from the Paris Observatory has run thousands of simulations of early solar system formation, and he notes, "In our models, we occasionally see planets that end up with tilted axes, but retrograde rotation is extraordinarily rare. Venus represents something that shouldn't happen according to our standard theories." The rarity of retrograde rotation becomes even more apparent when we look beyond our solar system. Of the thousands of exoplanets discovered by missions like Kepler and TESS, the vast majority that we can measure are rotating in the prograde direction. Retrograde rotation appears to be an anomaly that requires special explanation. This cosmic pattern extends beyond just the direction of rotation. The speed of planetary rotation also follows predictable trends based on a planet's formation history and subsequent evolution. Smaller rocky planets like Mercury and Mars rotate more slowly than Earth due to tidal forces from the Sun. Gas giants like Jupiter and Saturn spin rapidly because they formed from massive disks of material and have retained most of their original angular momentum. Venus should fit somewhere in this pattern. As Earth's twin in size and mass, formed at a similar distance from the Sun, Venus should rotate at a rate comparable to Earth's. Instead, it rotates more than 250 times slower and in the wrong direction entirely. The implications of this abnormal rotation extend far beyond simple curiosity. A planet's rotation affects its magnetic field, its atmospheric circulation, its climate stability, and even its ability to maintain surface conditions suitable for life. Venus's backwards, slow rotation contributes to its lack of a substantial magnetic field, leaving it vulnerable to the solar winds stripping away its atmosphere over geological time. Recent studies using data from the European Space Agency's Venus Express mission have revealed that Venus's slow rotation also affects its atmospheric dynamics in profound ways. The planet's thick atmosphere actually rotates much faster than the solid surface beneath it, creating a phenomenon called superrotation, where winds at high altitude circle the planet in just 4 days. This atmospheric superrotation is partly driven by the extreme temperature difference between Venus's day and night sides, a consequence of its slow rotation. The 117-day solar day means that each hemisphere of Venus experiences months of continuous sunlight followed by months of darkness, creating temperature gradients that drive massive atmospheric circulation patterns. But perhaps the most disturbing aspect of Venus's rotation is what it suggests about planetary stability. For over a century, astronomers assumed that once a planet forms and settles into its orbit, its basic properties like rotation rate and direction remain essentially constant over billions of years. Venus proves this assumption wrong. Something powerful enough to reverse an entire planet's rotation operated in our solar system's past. This force, whatever it was capable of overcoming the enormous rotational inertia of a planet nearly as massive as Earth. The physics involved are staggering. Venus has a moment of inertia of approximately 4.6 times kg square meter. To flip this backwards would require applying a torque, equivalent to the gravitational force of multiple Earth mass objects acting over thousands of years, or a single catastrophic event releasing energy comparable to the impact that created our moon. As we stand here contemplating this backwards world, we're forced to confront an unsettling reality. The solar system is not the stable, predictable clockwork we once imagined. It's a place where planets can be flipped upside down, where the fundamental rules of motion can be violated, where Earth's twin can be transformed into a hellish backward spinning world. The question that haunts planetary scientists is not just what caused Venus's retrograde rotation, but whether such forces could strike again. The evidence we'll explore suggests that the early solar system was a far more violent place than we ever imagined, and that this violence might not be entirely in the past. Chapter 2. Ancient Violence. The early solar system was a cosmic shooting gallery. For the first billion years after planetary formation, massive objects careened through space, colliding with devastating force, reshaping worlds and occasionally performing feats of destruction so complete they could flip an entire planet backwards. This period, known as the Late Heavy Bombardment, left scars across every solid surface in our solar system. The Moon's ancient highlands are saturated with impact craters. Mars bears the mark of collisions that created the largest impact basins in the solar system. Even Earth, despite billions of years of geological recycling, retains evidence of impacts massive enough to have sterilized the surface and boiled away the oceans. But Venus presents us with the most extreme case study in planetary violence. The evidence suggests that our sister planet was struck by an object so massive, and at such a precise angle that it completely reversed the planet-disk rotation. This wasn't just any collision. It was a cosmic catastrophe of almost unimaginable scale. Dr. Alistair Cameron, the late Harvard astrophysicist who pioneered the study of planetary collisions, calculated that reversing Earth's rotation would require an impactor with at least 1/10 our planet's mass, striking at precisely the right angle and velocity. For Venus, with its similar size and mass, the requirements would be equally extreme. Consider the physics involved. Venus rotates with an angular momentum of approximately 1.8 times ypkg square meter y in the retrograde direction. To flip it from an original prograde rotation would require first canceling out the original angular momentum, then adding enough energy to spin it backwards. The total energy involved would be equivalent to the kinetic energy of a Mars-sized object traveling at 20 kilometers per second. The Magellan radar mapping mission revealed crucial evidence for this collision scenario written across Venus's surface. The planet shows a global resurfacing event that occurred between 300 and 800 million years ago, erasing most traces of ancient impact craters. This massive volcanic resurfacing could be the long-term consequence of the collision that flipped Venus's rotation. Computer simulations by Dr. Robin Canop at the Southwest Research Institute demonstrate how such massive impacts can occur during planetary formation. In her models of the early solar system, Mars-sized objects called planetary embryos continued to exist for millions of years after the main phase of planetary accretion, occasionally colliding with the newly formed planets. These late-stage giant impacts were not rare events, explains Dr. Canop. Our simulations show that most terrestrial planets experienced at least one collision with an object larger than our Moon. Venus may have been unlucky enough to suffer a collision massive enough to flip its rotation. The timing of such an impact would be critical. If it occurred too early in Venus's history, subsequent accretion of material might have restored prograde rotation. If it happened too late, we would see more obvious signs of the impact on the current surface. The evidence suggests the collision occurred during a narrow window roughly 100 to 500 million years after Venus's formation. But here's where the story becomes even more remarkable. The impactor didn't just flip Venus's rotation and disappear. Depending on the angle and velocity of the collision, fragments of both Venus and the impactor would have been scattered throughout the inner solar system. Some of this material might have been captured by Earth, contributing to our planet's formation and perhaps even delivering the water that fills our oceans. The asteroid belt between Mars and Jupiter preserves evidence of this violent period in solar system history. Many asteroids show signs of catastrophic disruption. They were once larger objects that were shattered by massive collisions and later reassembled by gravity into loose piles of rubble. The Vesta asteroid, studied in detail by NASA's Dawn mission, shows impact basins so large they nearly shattered the entire object. These impacts occurred during the late heavy bombardment, demonstrating that objects large enough to flip planetary rotations were indeed careening through the inner solar system during this period. Recent analysis of lunar samples brought back by the Apollo missions has revealed that the Moon's ancient crust formed in a magma ocean created by the giant impact that formed our satellite. This impact, involving a Mars-sized object called Theia, shows that collisions capable of fundamentally altering planetary properties were not just possible but actually occurred in our solar system. The isotopic composition of Earth's mantle provides additional evidence for this chaotic period. Certain elements that should have been locked away in Earth's core during formation are found in the mantle, suggesting they were added by late-arriving impactors that struck after the core had already formed. Dr. Alessandro Morbidelli from the Observatoire de la Côte d'Azur has developed models showing how gravitational interactions with Jupiter and Saturn could have destabilized the orbits of planetary embryos, sending them on collision courses with the terrestrial planets. His research suggests that Venus's collision was not a random accident but part of a systematic reorganization of the solar system. The giant planets migrated during the first few 100 million years after formation, explains Dr. Morbidelli. This migration scattered objects throughout the inner solar system, creating a period of intense bombardment that reshaped all the terrestrial planets. The evidence for this migration comes from studying the asteroid belt and the outer solar system. The current orbital distribution of asteroids is unstable. Without the gravitational influence of migrating planets to place them in their current positions, they would have spiraled into the Sun or been ejected from the solar system long ago. The Trojan asteroids, which share Jupiter's orbit but are located 60 degrees ahead and behind the planet, were captured during this migration period. The capture process required precise timing and gravitational dynamics that only occurred when the giant planets were moving through the solar system. But perhaps the most compelling evidence for the collision scenario comes from Venus's current properties. The planet's extremely slow rotation and retrograde direction are exactly what we would expect from a massive oblique impact. Computer simulations show that head-on collisions tend to destroy both objects, while glancing blows can impart the specific combination of energy and angular momentum needed to flip a planet's rotation. The absence of a substantial moon around Venus also supports the collision hypothesis. While Earth's moon formed from debris ejected during the Theia impact, Venus's collision may have been even more violent, ejecting material at such high velocities that it escaped the planet's gravitational influence entirely. This violent origin story for Venus's rotation has profound implications for our understanding of planetary evolution. It suggests that the properties we observe today, rotation rate, axial tilt, magnetic field strength, may not reflect the original conditions during planetary formation, but rather the cumulative effects of billions of years of cosmic violence. The realization that planets can be fundamentally altered by single catastrophic events forces us to reconsider the stability of our own world. Earth has been struck by massive objects throughout its history, including the impact that killed the dinosaurs 66 million years ago. While that impact was devastating for life on the surface, it was nowhere near large enough to affect our planet's rotation. But the late heavy bombardment is not entirely over. Asteroids and comets continue to strike planets throughout the solar system, though at a much reduced rate compared to the early period. The impact that created the 180-kilometer-wide Chicxulub crater on Earth was caused by an object only 10 to 15 kilometers across. An object large enough to significantly affect Earth's rotation would be thousands of times more massive. As we piece together the evidence for Venus's violent past, we read confronted with a disturbing possibility. The cosmic forces that created a backward spinning world could strike again. While the probability of such an event in human timescales is vanishingly small, The geological record shows that our solar system has experienced violence on scales that dwarf anything in human experience. The backwards rotation of Venus stands as a permanent reminder that planets are not immune to cosmic catastrophe, that the basic properties we take for granted can be altered by forces beyond our comprehension, and that the universe is far more violent and unpredictable than our everyday experience suggests. Chapter 3. Impossible Mechanics. The mechanics of flipping an entire planet's rotation stretch the boundaries of what seems physically possible. To truly comprehend the forces involved in Venus's backward spin, we need to understand the staggering amount of energy required to overcome a planet's rotational inertia and reverse its motion entirely. Venus has a mass of 4.87 times y kilograms and a radius of 6,052 kilometers. When this massive sphere rotates, it possesses enormous angular momentum, the rotational equivalent of linear momentum. The angular momentum of a planet is determined not just by its mass, but by how that mass is distributed relative to the rotation axis. For a sphere like Venus, most of the mass is concentrated toward the center, but the outer layers still contribute significantly to the total angular momentum. Dr. David Stevenson from Caltech has calculated that Venus's current retrograde angular momentum represents approximately 1.8 times ypkg square meter, y of rotational energy. But here is what makes this number truly staggering. To flip Venus from its original prograde rotation to its current retrograde state would require canceling out the original angular momentum and then adding the reverse amount. The total energy change would be equivalent to 3.6 times ypkg square meters, y of angular momentum. To put this in perspective, imagine trying to stop a massive spinning top and then get it spinning in the opposite direction at the same rate. The force required would be proportional to the mass of the top, the square of its radius, and the change in rotation rate. For an object the size and mass of Venus, the forces involved are almost beyond comprehension. The impact energy required for such a collision would be approximately 1,032 joules. This is equivalent to the energy released by 100 billion nuclear weapons exploding simultaneously, or the total energy output of the sun for several hours. The impacting object would need to be roughly the size of Mars, traveling at speeds of 15 to 20 kilometers per second. Dr. Robin Canop's sophisticated computer simulations at the Southwest Research Institute model these giant impacts in exquisite detail. Her smooth particle hydrodynamics codes treat both Venus and the impactor as collections of thousands of particles, each following the laws of gravity, thermodynamics, and fluid mechanics as the collision unfolds. When we simulate a Mars-sized object hitting Venus at the right angle and velocity, we see exactly the kind of angular momentum transfer needed to explain the current rotation. Dr. Canop explains, but the collision is so violent that both objects are completely disrupted. What we call Venus today would have reformed from the debris cloud over thousands of years. The collision dynamics reveal why Venus's backwards rotation is so precise and stable. A random, chaotic impact would produce irregular rotation or cause the planet to tumble unpredictably. Instead, Venus rotates smoothly in a retrograde direction, suggesting that the angular momentum transfer was remarkably efficient. The key lies in the collision geometry. Computer models show that an oblique impact, where the impactor strikes at an angle of about 30 to 45 degrees from vertical, produces the optimal angular momentum transfer. The impactor's momentum is converted into rotational energy of the target, while minimizing the amount of material ejected from the system. But the impact scenario faces a significant challenge. The timing must be precisely right. If the collision occurred too early in Venus's formation, continued accretion of planetesimals would have altered the final rotation state. Too late, and the planet would have been too solid to efficiently transfer angular momentum. The geological evidence suggests that Venus experienced global resurfacing events that erased most impact craters from its surface. The most recent of these events occurred between 300 and 800 million years ago, far too recent to be the collision that flipped the planet's rotation. This means the impact must have occurred much earlier, possibly within the first 500 million years of Venus's existence. Recent research by Dr. Kaveh Palivan at the SETI Institute has revealed another crucial aspect of the collision mechanics. The impact would have created a massive debris disk around Venus, similar to the disk that formed Earth's moon after the Theia impact. However, Venus's proximity to the Sun creates unique conditions that could have prevented moon formation. The solar radiation pressure and tidal forces so close to the Sun would have dispersed any debris disk before a substantial moon could accumulate, explains Dr. Palivan. This explains why Venus lacks a large moon despite experiencing a moon-forming scale impact. The absence of a moon around Venus actually supports the collision theory. Earth's moon stabilizes our planet's axial tilt and helps maintain relatively stable climate conditions over geological time. Venus, without a large moon, has been free to evolve into its current extreme state. The collision mechanics also explain some of Venus's other unusual properties. The planet's lack of a substantial magnetic field could be a consequence of the massive impact. The collision would have reset Venus's thermal evolution, possibly preventing the development of the core convection needed to generate a magnetic dynamo. Dr. Ulrich Hansen from the University of Munster has modeled how giant impacts affect planetary thermal evolution. His research shows that the massive energy input from a collision can fundamentally alter a planet's internal structure and cooling history. The impact energy gets converted to heat throughout the planet. Dr. Hansen notes, this thermal resetting could delay or prevent the onset of core convection for billions of years, explaining why Venus lacks a magnetic field despite having a metallic core similar to Earth's. The collision scenario also addresses the puzzle of Venus's atmospheric composition. The planet's thick carbon dioxide atmosphere and extreme greenhouse effect might be partially explained by the massive impact. The collision could have vaporized large amounts of crustal material, releasing carbon dioxide that had been locked up in carbonate rocks. However, the collision mechanics face some theoretical challenges. The most significant is the problem of maintaining Venus's current slow rotation rate over billions of years. Tidal forces from the Sun should have altered Venus's rotation since the initial impact. Yet the planet maintains its precise 243-day period. Dr. Alexander Correa from the University of Aveiro has studied how tidal forces affect Venus's rotation over geological time. His calculations show that the current rotation state is actually close to an equilibrium condition where tidal torques from both the Sun and Venus's thick atmosphere are balanced. Venus may have evolved into a tidal equilibrium state regardless of its initial rotation, suggests Dr. Correa. This raises the possibility that the backwards rotation is not primarily due to a collision, but to long-term tidal evolution. This alternative explanation challenges the collision theory and suggests that the mechanics of Venus's rotation might be even more complex than a simple massive impact. The planet might have evolved into its current state through a combination of collision effects and subsequent tidal evolution over billions of years. The precision of Venus's current rotation, exactly 243.025 Earth days, suggests that some stabilizing mechanism has locked the planet into this specific state. The number is too exact to be the random result of a collision and subsequent chaotic evolution. Recent theoretical work has identified a possible resonance mechanism that could stabilize Venus's rotation. The planet's orbital motion around the Sun and its atmospheric circulation might interact in ways that naturally lead to the observed rotation period. As we grapple with these mechanical impossibilities, we're forced to confront the limitations of our understanding. The collision scenario explains many aspects of Venus's unusual rotation, but significant mysteries remain. The exact mechanisms that could flip a planet and then maintain that configuration for billions of years push the boundaries of planetary physics. The backwards rotation of Venus represents one of the most extreme examples of planetary mechanics in our solar system, a testament to the violent forces that can reshape worlds and the complex physics that govern planetary evolution over cosmic timescales. Chapter 4: Tidal Secrets. While massive collisions offer a dramatic explanation for Venus's backwards rotation, there exists a more subtle but equally fascinating possibility that our sister planet was slowly and inexorably flipped by the gentle but persistent force of gravity itself. The tidal forces that create Earth's ocean tides are far more powerful than most people realize, and over billions of years, they can fundamentally alter how planets spin. The story of tidal forces begins with the Moon pulling on Earth's oceans, but this is only the most visible effect of a much deeper gravitational interaction. Every planet experiences tidal forces from its parent star, and these forces can either speed up or slow down planetary rotation, depending on the specific orbital and rotational characteristics of the world in question. Dr. Jacques Lasker from the Paris Observatory has spent decades studying how tidal forces evolve planetary rotation over geological time. His research reveals that Venus's current rotation state might not be the result of a single catastrophic event, but rather the inevitable outcome of billions of years of gravitational interaction with the Sun. Tidal evolution is like a cosmic clock that runs very slowly, explains Dr. Lasker. Over millions of years, these forces can completely transform how a planet rotates. Venus might have started with normal rotation and gradually evolved into its current backward state through purely natural processes. The physics of tidal evolution depends on a planet's distance from its star, its rotation rate, and the strength of tidal dissipation within the planet itself. Venus orbits the Sun at an average distance of 108 million kilometers, placing it in a region where solar tidal forces are significantly stronger than those experienced by Earth. Moreover, Venus's thick atmosphere creates unique tidal dissipation effects that don't exist on other terrestrial planets. The massive atmospheric circulation patterns, driven by the extreme greenhouse effect, interact with the solid planet beneath in ways that can transfer angular momentum between the atmosphere and the surface. Dr. Gerald Schubert from UCLA has modeled how atmospheric tides on Venus could affect the planet's rotation over geological time. The planet's atmosphere rotates much faster than the solid surface, completing one revolution in just 4 days, compared to the surface's 243-day rotation period. This atmospheric superrotation creates enormous friction between the atmosphere and the surface, notes Dr. Schubert. Over billions of years, this friction could gradually slow down the planet's rotation and even reverse it under certain conditions. The mechanism works through atmospheric tidal bulges created by solar heating. As the Sun heats Venus's thick atmosphere, it creates pressure variations that form tide-like bulges in the gas. These atmospheric tides are offset from the direction of the Sun due to the atmosphere's circulation patterns, creating a torque that can alter the planet's rotation. Computer simulations show that this atmospheric tidal torque is currently acting to slow Venus's rotation even further. If we could wait another billion years, Venus might eventually become tidally locked to the Sun, with one hemisphere permanently facing our star and the other in eternal darkness. But here's where the tidal evolution theory becomes truly remarkable. The process is reversible under certain conditions. If Venus's atmosphere was different in the past, perhaps thinner, with different circulation patterns, the tidal forces might have acted in the opposite direction, gradually spinning the planet backwards from its original prograde rotation. Dr. Alexander Correa has identified a specific scenario where this could occur. If Venus originally had a thick atmosphere, but rotated faster than its current rate. Atmospheric tides could have first slowed the planet's rotation to zero, then continued to act until the planet was spinning slowly in the retrograde direction. The key is the relationship between the atmospheric circulation timescale and the planet's rotation period, explains Dr. Correa. When these timescales interact in specific ways, they can produce a torque that reverses planetary rotation without requiring any external collision. This tidal evolution scenario would explain several puzzling aspects of Venus's current state. The planet's rotation rate of exactly 243 Earth days is suspiciously close to a resonance condition where tidal forces are minimized. This suggests that Venus might have evolved into a stable equilibrium state where further tidal evolution is extremely slow. The theory also explains why Venus lacks a substantial magnetic field. Tidal evolution would have occurred gradually over billions of years, allowing the planet's internal structure to adjust slowly. This gradual process might have prevented the chaotic thermal conditions that could jumpstart a magnetic dynamo. Recent analysis of Venus's atmospheric composition provides additional support for the tidal evolution theory. The isotopic ratios of noble gases in Venus' atmosphere suggest that the planet has been losing atmospheric material to space for billions of years, primarily through interactions with the solar wind. Dr. David Grinspoon from the Planetary Science Institute has studied how atmospheric loss could affect tidal evolution. As Venus's atmosphere gradually becomes thinner due to solar wind stripping, the strength of atmospheric tides changes, potentially altering the direction and magnitude of tidal torques acting on the planet. Venus's atmospheric evolution and rotational evolution are coupled processes, notes Dr. Grinspoon. As the atmosphere changes, so does the planet's rotation, creating a complex feedback system that could explain the current backward spin. The tidal evolution theory faces some significant challenges, however. The most important is the timescale problem. Detailed calculations show that atmospheric tides alone might not be strong enough to completely reverse a planet's rotation within the age of the solar system. Dr. Caleb Scharf from Columbia University has calculated that reversing Earth's rotation through atmospheric tides alone would take tens of billions of years, longer than the universe has existed. Venus, being closer to the Sun, experiences stronger tidal forces, but even there, complete rotation reversal might require more time than available. The tidal evolution scenario is attractive because it doesn't require any catastrophic events, explains Dr. Scharf. But we need to be careful about the timescales involved. Venus may need a combination of tidal evolution and some external perturbation to explain its current rotation. This has led to hybrid theories that combine elements of both collision and tidal evolution. In these scenarios, Venus might have experienced a collision that altered its rotation, but not necessarily reversed it completely. Subsequent tidal evolution could have fine-tuned the planet's spin into its current precise retrograde state. The hybrid approach explains both the magnitude of Venus's rotation anomaly and its current stability. A collision provides the large angular momentum change needed to overcome the planet's rotational inertia, while tidal evolution explains the precise final state and ongoing stability of the rotation. Recent research has also identified additional tidal mechanisms that could affect Venus's rotation. The planet's slight orbital eccentricity creates varying tidal forces as Venus moves closer to and farther from the Sun during each orbit. These variations could create resonance effects that amplify the tidal torques beyond what would be expected from a perfectly circular orbit. Dr. Richard Greenberg from the University of Arizona has studied how orbital resonances can affect planetary rotation evolution. His work shows that even weak resonance effects can accumulate over geological time to produce significant changes in rotation states. Venus might have passed through various orbital resonances as the solar system evolved, suggests Dr. Greenberg. Each resonance crossing could have provided a boost to the tidal evolution process, making rotation reversal possible within the available timescales. The tidal evolution of Venus's rotation continues today, though at an almost imperceptibly slow rate. Precision measurements by radar astronomy show that Venus's rotation period is currently increasing by about 6.5 minutes per century due to ongoing atmospheric tidal effects. As we consider the tidal secrets hidden in Venus's rotation, we're reminded that planetary evolution operates on timescales so vast they challenge human comprehension. The gentle forces that create our ocean tides, acting over billions of years, might possess the power to flip entire worlds upside down, transforming the fundamental nature of planets through patience rather than violence. The tidal evolution of Venus represents a different kind of cosmic catastrophe, not the sudden violence of collision, but the inexorable force of gravity acting across cosmic time to reshape the very foundations of planetary motion. Chapter 5. Atmospheric prisoner Venus is wrapped in one of the most extreme atmospheres in the solar system, a crushing, acid-laden envelope that presses down with 92 times the force of Earth's atmosphere and reaches temperatures hot enough to melt lead. But this hellish atmosphere might hold the key to understanding Venus's backwards rotation, because it's doing something extraordinary. It's spinning independently of the planet beneath it, and this detachment could be slowly rewriting the laws of planetary motion. The discovery of atmospheric superrotation on Venus ranks among the most surprising findings in planetary science. While Venus's solid surface completes one rotation every 243 Earth days, the upper atmosphere races around the planet in just 4 Earth days. This means the atmosphere is moving roughly 60 times faster than the surface, creating winds that reach speeds of 120 meters per second at altitude, faster than the strongest hurricanes on Earth. Dr. Kevin McGoldrick from the University of Colorado has studied Venus's atmospheric dynamics using data from multiple spacecraft missions. His research reveals that this superrotation is maintained by complex interactions between solar heating, atmospheric circulation, and the planet's slow rotation. Venus's atmosphere has essentially decoupled from the solid planet, explains Dr. McGoldrick. It's like having a massive fluid envelope that's free to rotate at its own rate, independent of the rocky world beneath it. This creates unique opportunities for angular momentum exchange between the atmosphere and the defies surface. The physics of this atmospheric decoupling begins with Venus's extreme greenhouse effect. The planet's thick carbon dioxide atmosphere traps solar energy so efficiently that surface temperatures reach 464 degrees Celsius, hot enough to melt zinc. This intense heating drives convection currents that transport energy from the day side to the night side of the planet. But here's where Venus's slow rotation creates a crucial difference from Earth. The planet has 117 day-long solar day, means that each hemisphere experiences months of continuous heating followed by months of cooling. This extreme day-night cycle drives atmospheric circulation patterns unlike anything seen on other planets. The European Space Agency's Venus Express mission, which studied the planet from 2006 to 2014, provided unprecedented insights into how this atmospheric circulation works. The spacecraft revealed that Venus's atmosphere is organized into distinct circulation cells, with rising motion on the day side and sinking motion on the night side. Dr. Giuseppe Piccioni from the Italian National Institute for Astrophysics led many of the Venus Express atmospheric studies. His research shows that the superrotating atmosphere is driven by a combination of thermal tides and momentum transport processes that are unique to slow-rotating planets with thick atmospheres. The slow rotation allows thermal tides to dominate over Coriolis effects, notes Dr. Piccioni. This creates atmospheric circulation patterns that can efficiently transport angular momentum from the equator to the poles and between different altitude levels. This atmospheric angular momentum transport has profound implications for Venus's rotation evolution. The atmosphere contains approximately 140 times more angular momentum than the solid planet, despite having only 1/100th the mass. This enormous atmospheric reservoir of angular momentum is constantly interacting with the surface through friction and pressure effects. Computer models developed by Dr. Mark Lewis at the University of Oxford show how atmospheric friction can transfer angular momentum between Venus' atmosphere and surface over geological time. The direction and magnitude of this transfer depends critically on the relative rotation rates of the atmosphere and surface. When the atmosphere rotates faster than the surface, friction acts to spin up the surface and slow down the atmosphere, explains Dr. Lewis. But the reverse is also possible. If conditions were different in the past, atmospheric friction could have spun down the surface and even reversed its rotation direction. The key to this mechanism lies in Venus's unique atmospheric structure. Unlike Earth, where most atmospheric mass is concentrated near the surface, Venus's dense atmosphere extends to high altitudes. This creates multiple layers where different circulation patterns can develop, each potentially exchanging angular momentum with the others and with the solid planet. Recent research has identified specific atmospheric processes that could drive rotation reversal. Thermal tides created by solar heating generate atmospheric motions that are offset from the direction of the sun due to the atmosphere's superrotation. This offset creates a net torque on the planet that currently acts to slow down Venus' already slow rotation. Dr. Sebastian Leibenhuis from the Laboratoire de Meteorologie Dynamique has modeled how these atmospheric torques have evolved over Venus' history. His research suggests that the strength and direction of atmospheric torques depends sensitively on the planet's atmospheric composition and rotation rate. Early in Venus's history, when the atmosphere might have been thinner and the planet rotating faster, atmospheric torques could have acted in the opposite direction, suggests Dr. Leibenhuis. Over billions of years, these torques could have gradually slowed the planet's rotation, stopped it, and then spun it up in the reverse direction. This atmospheric evolution scenario explains several puzzling aspects of Venus's current state. The planet's rotation period of 243 Earth days is remarkably close to a resonance condition where atmospheric and gravitational torques nearly cancel each other out. This suggests that Venus has evolved into a quasi-equilibrium state where further rotation changes occur very slowly. The scenario also explains the precise relationship between Venus's rotation and orbital periods. The planet rotates exactly 1.625 times per Venus year, a ratio that seems too precise to be coincidental. This relationship might result from a complex resonance between atmospheric circulation, gravitational tides, and orbital motion. But perhaps the most remarkable aspect of the atmospheric theory is its prediction that Venus' rotation could continue to evolve. Current atmospheric torques are still acting to slow down the planet's rotation, suggesting that Venus might eventually become tidally locked to the Sun, with one hemisphere permanently facing our star. Dr. Steve Lee from the University of Colorado has calculated that this tidal locking process could occur within the next billion years if current atmospheric conditions persist. However, Venus's atmospheric evolution is itself driven by ongoing processes like atmospheric escape and volcanism, making long-term predictions uncertain. The atmospheric evolution of Venus' rotation represents a fundamentally different type of planetary dynamics from what we observe elsewhere in the solar system. Most planets maintain relatively stable rotation rates over geological time, but Venus appears to be actively evolving, driven by the complex feedback between its extreme atmosphere and its slow rotation. This atmospheric coupling also affects Venus' climate evolution in ways that might be relevant to understanding climate change on Earth. The relationship between atmospheric circulation and planetary rotation creates feedback loops that can amplify or dampen climate perturbations over geological time. Recent studies using the Japanese Akatsuki spacecraft, which entered Venus orbit in 2015, have revealed additional complexity in the planet's atmospheric dynamics. The spacecraft has observed atmospheric gravity waves, thermal tides, and circulation patterns that vary on timescales from days to years. Dr. Takeshi Imamura from the University of Tokyo leads the Akatsuki Atmospheric Science Team. His research is uncovering new aspects of Venus's atmospheric dynamics that could affect rotation evolution. We're finding that Venus's atmosphere is far more variable and complex than we expected. The superrotation itself varies in strength over time, which could affect the atmospheric torques acting on the planet. These variations in atmospheric dynamics suggest that Venus's rotation evolution might not follow a smooth, predictable path. Instead, the planet might experience periods of rapid change interspersed with periods of relative stability, depending on how atmospheric circulation patterns evolve in response to solar forcing and internal heat sources. The atmospheric prisoner scenario for Venus's rotation presents us with a planet trapped by its own extreme climate. The thick atmosphere that makes Venus a hellish world also serves as a massive reservoir of angular momentum that can slowly but inexorably alter the planet's spin over cosmic time. This atmospheric control of planetary rotation challenges our traditional understanding of planetary mechanics and suggests that climate and rotation evolution are far more intimately connected than previously thought. Venus shows us that atmospheres are not passive envelopes around planets, but active participants in planetary evolution, capable of rewriting the fundamental properties of the worlds they surround. Chapter 6. Resonance Mystery. Hidden within the mathematics of planetary motion lies one of the most extraordinary discoveries about Venus's backwards rotation. The planet appears to be locked in an intricate gravitational dance with Earth that occurs with clockwork precision every time our two worlds align. This celestial choreography, known as a spin-orbit resonance, suggests that Venus's rotation might not be a cosmic accident, but rather the inevitable result of billions of years of gravitational fine-tuning between neighboring worlds. The discovery began with a seemingly mundane observation. Every time Venus and Earth reach their closest approach during Venus's inferior conjunction, the same hemisphere of Venus faces Earth. This means that Earth-based radar observations consistently map the same regions of Venus's surface during these optimal observation periods. Dr. Stan Ostro from NASA's Jet Propulsion Laboratory first noticed this pattern while analyzing decades of radar data from the Goldstone and Arecibo observatories. The precision was remarkable. Despite Venus's complex orbital mechanics and slow rotation, the planet consistently presented nearly identical faces to Earth during close approaches, with variations of less than 2 degrees. The probability of this happening by chance is essentially zero, explains Dr. Ostro. We're looking at a resonance relationship that locks Venus's rotation to its orbital relationship with Earth in a way that shouldn't be possible for planets separated by tens of millions of kilometers. The mathematics of this resonance are both elegant and mysterious. Venus's rotation period of 243.025 Earth days creates a precise relationship with Earth's orbital period such that exactly 5 Venus rotations equal 8 Earth-Venus synodic periods, the time between successive close approaches. This 5 to 8 resonance means that Venus rotates exactly 5 times while Earth and Venus complete 8 orbital cycles relative to each other. To understand how extraordinary this is, consider that Venus's rotation period would need to be precise to within a few hours out of 243 days for this resonance to work. The gravitational forces involved are incredibly weak. Earth's tidal influence on Venus is roughly 100,000 times smaller than the Sun's influence. Yet somehow, This tiny force appears to have locked Venus into an exact rotational relationship with Earth. Dr. Carl Murray from Queen Mary, University of London, has studied similar resonance relationships throughout the solar system. His research shows that while spin-orbit resonances are common among moons orbiting planets, they are extraordinarily rare between planets themselves. Planetary spin-orbit resonances require very specific conditions to form and maintain, notes Dr. Murray. The fact that Venus appears to be in resonance with Earth suggests either an incredible coincidence or a mechanism we don't fully understand yet. The resonance becomes even more puzzling when we consider its stability. Computer simulations show that Venus' rotation should be unstable over millions of years due to gravitational perturbations from other planets, particularly Jupiter. These perturbations should gradually shift Venus's rotation period, breaking any resonance with Earth. Yet the resonance persists, suggesting the existence of a stabilizing mechanism that can overcome these perturbations. Dr. Alexander Correa from the University of Aveiro has proposed that Venus' thick atmosphere might provide this stabilization through atmospheric tidal effects that adjust the planet's rotation to maintain the resonance. Atmospheric tides can act like a feedback system, explains Dr. Correa. If gravitational perturbations try to shift Venus out of resonance, atmospheric torques could automatically adjust to pull it back into the exact resonance relationship. This atmospheric stabilization mechanism would require Venus' atmosphere to be exquisitely sensitive to small changes in rotation rate. Recent studies of atmospheric superrotation suggest that this sensitivity might indeed exist, as the atmospheric circulation patterns that drive superrotation are closely coupled to the planet's rotation rate. But here's where the mystery deepens. If Venus is truly locked in resonance with Earth, this relationship might explain not just the planet's current rotation rate, but also its retrograde direction. Resonance capture typically occurs when tidal forces gradually slow a planet's rotation until it becomes trapped in a specific ratio with its orbital motion. For Venus, this process might have worked differently due to the planet's proximity to the Sun. Strong solar tides could have first slowed Venus's original prograde rotation to near zero, creating conditions where the weak but persistent tidal influence from Earth could capture the planet into retrograde resonance. Dr. Bruce Bills from NASA's Jet Propulsion Laboratory has modeled this resonance capture process using advanced celestial mechanics simulations. His research suggests that the capture could occur if Venus' rotation was slowed by solar tides to within a narrow range of rotation rates. The Earth-Venus resonance represents a kind of gravitational fossil, explains Dr. Bills. Once established, the resonance becomes self-maintaining and can persist for billions of years, preserving evidence of the exact orbital configuration that existed when the resonance was captured. This resonance capture scenario would require Venus to have passed through a specific rotation rate at exactly the right time in its orbital evolution. The probability of this occurring naturally seems vanishingly small, yet the observational evidence for the resonance is compelling. Alternative theories suggest that the resonance might be a more recent phenomenon, established within the last few 100 million years due to changes in Venus' atmospheric properties or orbital evolution. The planet's massive volcanic resurfacing events could have temporarily altered its moment of inertia, creating opportunities for resonance capture. Recent studies using data from the European Space Agency's Venus Express mission have revealed that Venus's atmospheric mass and circulation patterns show long-term variations that could affect the planet's rotational dynamics. These atmospheric changes might periodically reset the resonance relationship with Earth. Dr. Giuseppe Piccioni from the Italian National Institute for Astrophysics has analyzed Venus Express data for evidence of resonance effects. His research suggests that the atmospheric superrotation itself might be influenced by the Earth-Venus resonance, creating atmospheric circulation patterns that help maintain the precise rotation rate. We're seeing correlations between Venus's atmospheric dynamics and its resonance relationship with Earth that suggest these systems are coupled in ways we're only beginning to understand, notes Dr. Piccioni. The implications of the Earth-Venus resonance extend far beyond explaining Venus's backwards rotation. If confirmed, this relationship would represent one of the most remarkable examples of long-range gravitational coupling in the solar system, demonstrating that planetary evolution can be influenced by forces operating over vast distances and timescales. The resonance also raises profound questions about the predictability of planetary evolution. If two planets can influence each other's rotation across tens of millions of kilometers of space, then planetary systems might be far more interconnected than we previously imagined. This interconnectedness could have implications for understanding exoplanetary systems, where multiple planets often orbit much closer to their stars than planets in our solar system. In such systems, resonance relationships might play crucial roles in determining planetary rotation rates and climatic evolution. Dr. Sean Raymond from the University of Bordeaux has studied resonance relationships in exoplanetary systems discovered by the Kepler Space Telescope. His research suggests that spin-orbit resonances might be common in systems with closely packed planets, potentially affecting the rotation states and atmospheric evolution of these worlds. The Venus-Earth resonance might be giving us a preview of the types of gravitational interactions that dominate planetary evolution in other stellar systems, suggests Dr. Raymond. Understanding this relationship could help us predict the rotation states and climatic properties of exoplanets. The resonance mystery also challenges our understanding of how planetary systems achieve stability. Traditional models assume that planetary rotations evolve independently, influenced mainly by each planet's individual tidal environment. The Earth-Venus resonance suggests that planets might collectively evolve toward configurations that minimize the total energy of the system. As we continue to study this gravitational dance between Earth and Venus, we are confronted with the possibility that our solar system is far more carefully choreographed than we ever imagined. The backwards rotation of Venus might not be a cosmic accident, but rather evidence of a hidden harmony that connects the motion of worlds across the vast emptiness of space. This resonance represents a different kind of cosmic order, not the chaotic violence of collisions or the inexorable pull of tides, but the subtle mathematics of gravitational harmony that can emerge from billions of years of planetary interaction. Chapter 7. Solar Influence. The Sun's influence on planetary rotation extends far beyond the obvious effects of solar heating and gravitational attraction. For Venus, orbiting at just 72% of Earth's distance from our star, the solar environment creates unique conditions that could fundamentally alter how the planet spins. The combination of intense solar radiation pressure, magnetic field interactions, and tidal forces creates a complex web of influences that might explain Venus's backwards rotation through purely solar mechanisms. Solar radiation pressure, while incredibly weak compared to gravitational forces, becomes significant for objects with large surface area to mass ratios or over very long time periods. Venus presents both characteristics. Its thick atmosphere extends far into space, creating an enormous effective surface area exposed to solar radiation, while geological timescales allow even minute forces to accumulate dramatic effects. Dr. Joseph Burns from Cornell University has studied how solar radiation pressure affects planetary rotation throughout the solar system. His research reveals that radiation pressure can create asymmetric forces on planets with atmospheres, particularly when atmospheric density varies between the day and night sides. Venus's extremely long day creates the most extreme day-night temperature differences of any planet, explains Dr. Burns. This temperature difference drives atmospheric expansion on the day side and contraction on the night side, creating an asymmetric target for solar radiation pressure that can generate turquoise on the entire planet. The mechanism works through what physicists call the Yarkovsky effect, named after the Russian engineer Ivan Yarkovsky, who first described how solar heating can alter the orbits of small asteroids. For Venus, the effect operates on the planet's thick atmosphere, which absorbs solar energy during the day and re-radiates it as thermal infrared radiation during both day and night. The crucial factor is timing. Venus' slow rotation means that atmospheric heating and cooling cycles are not synchronized with the planet's rotation. Hot atmospheric regions face away from the Sun, creating a net torque that can either accelerate or decelerate the planet's rotation depending on the specific atmospheric properties and circulation patterns. Computer simulations by Dr. David Rubingham from NASA's Goddard Space Flight Center show that this atmospheric Yarkovsky effect could be strong enough to significantly alter Venus's rotation over billions of years. The direction of the effect depends on the atmospheric thermal inertia and the planet's rotation rate. If Venus originally rotated faster, the thermal lag effect would create a torque opposing the rotation, explains Dr. Rubingham. Over geological time, this could slow the planet's rotation to zero and then continue to act, spinning the planet up in the opposite direction. But solar influence extends beyond radiation pressure to include the complex interactions between Venus' ionosphere and the solar magnetic field. Unlike Earth, Venus lacks a substantial magnetic field of its own, leaving its upper atmosphere directly exposed to the solar wind. The stream of charged particles flowing outward from the Sun, the European Space Agency's Venus Express mission revealed that Venus' ionosphere undergoes dramatic changes as the solar wind interacts directly with the planet's upper atmosphere. This interaction creates electric currents in the ionosphere that can couple to the lower atmosphere through electromagnetic forces. Dr. Tilong Zhang from the Austrian Academy of Sciences led studies of Venus's magnetic environment using Venus Express data. His research shows that the planet's interaction with the solar magnetic field creates asymmetric forces that vary with solar activity and the planet's position in its orbit. Venus essentially acts like a conducting sphere moving through the solar magnetic field, notes Dr. Zhang. This generates electric currents that create forces opposing the planet's motion, both orbital and rotational. Over geological time, these forces could significantly alter planetary rotation. The solar magnetic field interaction becomes particularly important during periods of high solar activity. When the Sun experiences flares and coronal mass ejections, the enhanced solar wind can dramatically increase the electromagnetic forces acting on Venus's ionosphere. Paleomagnetic studies of Earth's geological record show that the Sun's magnetic activity has varied significantly over the past few billion years. During periods when the young Sun was more magnetically active, the electromagnetic forces on Venus would have been correspondingly stronger, potentially accelerating the alteration of the planet's rotation. Dr. Kristina Kizliakova from the University of Vienna has modeled how enhanced solar activity in the early solar system could have affected Venus's atmospheric and rotational evolution. Her research suggests that the young Sun's stronger magnetic field and more intense solar wind could have stripped away portions of Venus's early atmosphere while simultaneously altering the planet's rotation through electromagnetic torques. The early Sun was much more active than today, with magnetic field strengths possibly 10 times greater, explains Dr. Kislyakova. This enhanced activity could have created electromagnetic forces on Venus strong enough to influence its rotation evolution over hundreds of millions of years. Solar tidal forces represent another mechanism by which the Sun could have influenced Venus's rotation. While these forces are typically much weaker than collision effects, they operate continuously over billions of years and can accumulate significant changes in planetary rotation states. For Venus, solar tides are complicated by the planet's elliptical orbit and its thick atmosphere. As Venus moves closer to and farther from the Sun during each orbit, the varying tidal forces create a pumping action that can gradually alter the planet's rotation rate and direction. Dr. Jacques Lasker from the Paris Observatory has calculated that solar tidal forces on Venus are enhanced by the planet's atmospheric mass and extent. The thick atmosphere effectively increases Venus's tidal response, making it more susceptible to solar tidal effects than a planet with a thin atmosphere would be. Venus's massive atmosphere acts like a tidal amplifier, explains Dr. Lasker. The atmospheric tidal response to solar forcing is much stronger than the solid body tides, creating opportunities for the Sun to influence the planet's rotation more effectively than we might expect. Recent research has also identified feedback mechanisms between solar influences and Venus's atmospheric evolution that could amplify the effects on rotation. As solar radiation pressure and electromagnetic forces alter the planet's rotation, they also affect atmospheric circulation patterns, which in turn modify how the atmosphere responds to solar influences. This feedback coupling creates the possibility for runaway evolution, where small initial changes in rotation rate are amplified by atmospheric responses, leading to dramatic changes in planetary spin over geological timescales. Dr. Stephen Bauer from the University of Michigan has studied these feedback mechanisms using sophisticated atmospheric circulation models. His research shows that changes in Venus's rotation rate affect the planet's atmospheric superrotation, which in turn affects how the atmosphere responds to solar heating and electromagnetic forces. Venus's rotation and atmospheric circulation are coupled systems that can evolve together in response to solar influences, notes Dr. Bauer. Small changes in one can lead to large changes in the other, creating the potential for rapid evolutionary transitions in the planet's rotation state. The solar influence scenario for Venus as backwards rotation gains support from observations of atmospheric escape from the planet. Both the Pioneer Venus and Venus Express missions have detected ions and neutral atoms streaming away from Venus's upper atmosphere, driven by solar wind interactions. This atmospheric loss process could affect the planet's rotation by changing its moment of inertia over geological time. As Venus loses atmospheric mass, the remaining planet becomes easier to spin up or slow down through external torques, potentially accelerating rotation evolution. Dr. Daryl Strobel from Johns Hopkins University has calculated the rate of atmospheric loss from Venus and its potential effects on rotation evolution. His research suggests that Venus has lost the equivalent of several Earth atmospheres over the past few billion years, significantly altering the planet's rotational dynamics. Atmospheric escape changes the mass distribution of the Venus system, explains Dr. Strobel. As the atmosphere becomes thinner, the coupling between atmospheric and solid body rotation changes, potentially triggering transitions in rotation state. The combination of radiation pressure, electromagnetic forces, tidal effects, and atmospheric loss creates a complex solar environment that could gradually transform Venus's rotation over billions of years. Unlike the sudden violence of collision scenarios, solar influence represents a gradual but inexorable force that could reshape planetary rotation through persistence rather than catastrophe. This solar influence model explains Venus's backwards rotation as the natural result of the planet's proximity to the Sun and its unique atmospheric properties. It suggests that any planet with similar characteristics orbiting at Venus's distance would eventually evolve similar rotation anomalies, making backwards rotation not a cosmic accident but a predictable outcome of solar system dynamics. Chapter 8. Hidden Clues. The true story of Venus's backwards rotation is written in a cosmic code scattered across our solar system. Hidden in the geological records of distant moons, the orbital patterns of asteroids, and the chemical signatures locked within meteorites that have journeyed across space to reach Earth. These hidden clues, when assembled like pieces of an ancient puzzle, reveal that Venus's rotation reversal was not an isolated event but part of a larger pattern of violence and transformation that reshaped the inner solar system billions of years ago. The first set of clues comes from Venus itself, etched into the planet's surface by processes that occurred long after its rotation was reversed. The Magellan radar mapping mission revealed that Venus's surface is remarkably young geologically, with an average age of only 300 to 800 million years. This global resurfacing event erased most of the ancient impact craters that should mark Venus's early history, but it also preserved crucial evidence about the planet's rotational past. Dr. Gerald Schubert from UCLA has analyzed the geological structures revealed by Magellan's radar maps, focusing on features that could preserve information about Venus's ancient rotation. His research has identified subtle patterns in the planet's tectonic features that suggest Venus once rotated much faster than it does today. The orientation of certain tectonic structures on Venus appears to be inconsistent with the planet's current slow rotation, explains Dr. Schubert. These features seem to have formed when Venus was spinning faster, possibly in the opposite direction, preserving evidence of the planet's rotational history in its geological record. The most compelling evidence comes from Venus's largest impact craters, which are among the youngest features on the planet's surface. These craters show asymmetric ejecta patterns that don't align with Venus's current rotation direction, suggesting they formed when the planet was rotating differently. Dr. Ellen Stofan, former NASA chief scientist, has studied these crater asymmetries in detail. Her analysis reveals that the ejecta patterns are consistent with formation during prograde rotation at a much faster rate than Venus's current spin. The crater evidence suggests that Venus experienced its rotation reversal before the global resurfacing event, but after some of its largest impact craters formed, notes Dr. Stofan. This gives us a time frame for when the rotation reversal occurred, and confirms that it was a real event, not just a theoretical possibility. Beyond Venus itself, the most dramatic clues come from the asteroid belt, where we find the shattered remnants of objects that witnessed the early solar system's violence firsthand. The asteroid 4 Vesta, studied in detail by NASA's Dawn mission, bears scars from impacts so massive they nearly destroyed the entire object. Dr. Christopher Russell from UCLA led the Dawn mission's scientific investigations. His team's analysis of Vesta's impact basins revealed that the asteroid experienced multiple catastrophic collisions during a period roughly coincident with when Venus's rotation reversal likely occurred. Vesta's impact history tells us that Mars-sized objects were careening through the inner solar system during the first few hundred million years after planetary formation, explains Dr. Russell. These are exactly the types of objects that could have collided with Venus and reversed its rotation. The timing evidence is particularly compelling. Radiometric dating of meteorites that originated from Vesta's impact events shows that the most catastrophic collisions occurred between 4.1 and 4.5 billion years ago, during the late heavy bombardment period, when Venus likely experienced its rotation reversal. But perhaps the most surprising clues come from Earth's moon, whose ancient highland rocks preserve a record of the violent processes that shaped the inner solar system. The Apollo samples revealed that the moon formed from debris created by a Mars-sized impact on the early Earth, demonstrating that planet-altering collisions were not just possible but actually occurred in our solar system. Dr. Robin Canup from the Southwest Research Institute has analyzed the lunar evidence for giant impacts throughout the inner solar system. Her research shows that the same population of Mars-sized objects that created our moon would have posed a significant collision threat to Venus over the first few hundred million years of solar system history. The moon's existence proves that objects large enough to flip planetary rotations were present in the inner solar system during its early history, notes Dr. Canup. Venus, being closer to the chaotic inner regions, would have been even more likely to experience such collisions than Earth. Chemical analysis of lunar rocks has revealed another crucial clue: the presence of elements that were likely delivered by late-arriving impactors after the Moon's initial formation. These chemical signatures match those found in certain types of meteorites, suggesting that similar material was being scattered throughout the inner solar system during the late heavy bombardment. The asteroid belt preserves additional evidence in the form of collision families, groups of asteroids that formed when larger objects were shattered by massive impacts. Computer simulations show that these collision families formed during discrete time periods, with the largest events occurring during the same era when Venus's rotation reversal likely happened. Dr. Alessandro Morbidelli from the Observatoire de la Côte d'Azur has studied these asteroid families to understand the dynamics of the early solar system. His research reveals that the late heavy bombardment was triggered by the migration of Jupiter and Saturn, which destabilized the orbits of numerous Mars-sized objects and sent them careening toward the inner planets. The asteroid belt evidence shows that the period when Venus's rotation was reversed was characterized by unprecedented levels of collisional activity, explains Dr. Morbidelli. This wasn't a random event, but part of a systematic reorganization of the entire solar system. Meteorite evidence provides even more detailed clues about the conditions during this chaotic period. Certain types of meteorites, particularly the abrites and uralites, show evidence of having been shocked and heated to extreme temperatures during massive collisions. The timing of these shock events, determined through radiometric dating, correlates closely with the period when Venus's rotation reversal occurred. Dr. Timothy McCoy from the Smithsonian Institution has analyzed these shock signatures in meteorites. His research reveals that the early solar system experienced a period of intense collisional heating that affected objects throughout the inner solar system. The meteorite evidence tells us that the early solar system was a much more violent place than we see today, notes Dr. McCoy. The shock signatures we observe are consistent with the types of massive collisions that could reverse planetary rotations. Recent discoveries have revealed additional clues hidden in the most unexpected places. The Martian meteorites that have landed on Earth preserve evidence of massive impacts on Mars during the same period when Venus's rotation was reversed. These impacts were so powerful they ejected material that eventually reached Earth, carrying with it a record of the violence that characterized the early inner solar system. Dr. Harry McSween from the University of Tennessee has studied these Martian meteorites for evidence of ancient impact events. His analysis reveals that Mars experienced its largest impacts during the late heavy bombardment, suggesting that the same population of objects that may have reversed Venus's rotation also bombarded Mars. The Martian meteorite evidence shows that the entire inner solar system was under assault during this period, explains Dr. McSween. No planet was safe from the massive objects that were ricocheting through the inner solar system. Perhaps the most intriguing clues come from the isotopic composition of Venus's atmosphere, which can be measured by Earth-based spectroscopy and spacecraft observations. The ratios of different isotopes of noble gases in Venus' atmosphere provide information about the planet's early evolution and any major events that might have affected its atmospheric history. Dr. Hunter Waite from the Southwest Research Institute has analyzed these atmospheric isotope ratios using data from multiple Venus missions. His research suggests that Venus experienced a major atmospheric disruption event that could be consistent with a massive impact. Venus's atmospheric isotope ratios are different from what we'd expect for a planet that evolved peacefully, notes Dr. Waite. The signatures we observe could be explained by a massive impact that temporarily disrupted or removed parts of the atmosphere. The hidden clues scattered throughout our solar system paint a picture of an early period of unprecedented violence, when Mars-sized objects routinely collided with planets, shattering moons, reversing rotations, and fundamentally altering the architecture of the inner solar system. Venus's backwards rotation stands as perhaps the most dramatic surviving evidence of this cosmic catastrophe, a permanent reminder that even planets are not immune to the forces of destruction that operate throughout the universe. These clues force us to confront the reality that the solar system we observe today is not the peaceful, stable system it appears to be, but rather the scarred survivor of a period of violence so extreme it challenges our understanding of planetary formation and evolution. Chapter 9. Evolutionary Pathways. Venus's backwards rotation represents just one possible outcome in the vast space of planetary evolutionary pathways, each determined by the complex interplay of formation conditions, orbital dynamics, and cosmic accidents that shape worlds over billions of years. Understanding these pathways reveals that Venus's fate was not inevitable, but rather the result of a specific sequence of events that could have unfolded differently, creating alternative histories where Venus might have remained Earth's true twin. The concept of evolutionary pathways in planetary science emerged from the recognition that small changes in initial conditions can lead to dramatically different outcomes over geological time. This principle, known as sensitive dependence on initial conditions, means that Venus could have easily evolved into a world very different from the hellish, backward spinning planet we observe today. Dr. James Casting from Penn State University has developed comprehensive models of planetary evolution that explore how different initial conditions lead to different planetary outcomes. His research reveals that Venus began its evolution in the habitable zone around the Sun, with conditions that could have supported liquid water and possibly life for billions of years. Venus and Earth started as remarkably similar worlds, explains Dr. Casting. The fact that they evolved so differently demonstrates how sensitive planetary evolution is to subtle differences in initial conditions and subsequent evolutionary events. The earliest pathway divergence between Earth and Venus likely occurred within the first few 100 million years of their formation. Both planets formed from similar materials in the same region of the solar nebula, but small differences in their accretion histories created initial conditions that would ultimately lead to vastly different evolutionary trajectories. Computer simulations by Dr. Sean Raymond from the University of Bordeaux show that Venus could have ended up with a different rotation state if its formation had proceeded slightly differently. In some simulations, Venus retains normal prograde rotation and evolves into an Earth-like world with oceans and a stable climate. The parameter space for planetary evolution is enormous, notes Dr. Raymond. Venus represents just one possible outcome among thousands of alternative evolutionary pathways that could have produced very different worlds. The rotation reversal event itself created a major branching point in Venus's evolutionary pathway. Before this event, Venus likely had a rotation rate similar to Earth's, generating a magnetic field through core convection and maintaining atmospheric conditions that could support surface water. Dr. David Grinspoon from the Planetary Science Institute has modeled how Venus's evolution would have proceeded without the rotation reversal. His research suggests that Venus could have maintained habitable conditions for billions of years, potentially developing complex life and avoiding the runaway greenhouse effect that characterizes the planet today. The rotation reversal may have been the single event that doomed Venus to its current state, explains Dr. Grinspoon. Without it, Venus might still be a blue world with oceans, possibly harboring life that evolved independently from Earth. The loss of Venus's magnetic field following the rotation reversal created a cascade of evolutionary changes that transformed the planet's atmosphere and surface conditions. Without magnetic protection, Venus's atmosphere became vulnerable to solar wind stripping, while the slow rotation rate prevented the regeneration of core convection needed to restart the magnetic dynamo. This atmospheric vulnerability led to the gradual loss of hydrogen from water vapor in Venus's upper atmosphere, concentrating deuterium and creating the heavy water signature we observe today. The loss of water vapor, combined with increased volcanic outgassing, due to the planet's thermal evolution, drove the atmospheric composition toward the carbon dioxide-dominated greenhouse we see today. Recent research has identified alternative evolutionary pathways where Venus could have avoided this fate even after experiencing rotation reversal. Dr. Colin Goldblatt from the University of Victoria has modeled scenarios where Venus maintains surface water despite slow, retrograde rotation. If Venus had started with a thicker atmosphere or different volatile inventory, it might have been able to compensate for the effects of rotation reversal, suggests Dr. Goldblatt. There are evolutionary pathways where backwards rotation doesn't necessarily lead to the loss of habitability. The timing of major evolutionary transitions also played a crucial role in determining Venus's final state. The planet's massive volcanic resurfacing events, which occurred between 300 and 800 million years ago, might have been triggered or influenced by the long-term effects of rotation reversal on the planet's internal dynamics. Dr. Suzanne Smarker from NASA's Jet Propulsion Laboratory has studied how rotation reversal could affect the planet's internal evolution. Her research suggests that the massive energy input from the impact or process that reversed Venus's rotation could have fundamentally altered the planet's thermal evolution and volcanism patterns. Venus's geological evolution has been shaped by its rotation anomaly in ways we're only beginning to understand. Notes Dr. Smarker, the planet's current volcanic and tectonic activity might be direct consequences of events that occurred billions of years ago. The atmospheric evolutionary pathway taken by Venus also depends critically on the planet's distance from the Sun. At 0.72 astronomical units, Venus receives about twice as much solar energy as Earth, placing it near the inner edge of the habitable zone where greenhouse effects can rapidly lead to water loss and atmospheric transformation. However, alternative evolutionary pathways exist even at Venus's orbital distance. Dr. Ravi Kalparapu from NASA's Goddard Space Flight Center has identified atmospheric compositions and rotation states that could maintain habitable conditions at Venus's orbital distance, suggesting that the planet's current state was not inevitable. Venus's proximity to the Sun makes it challenging but not impossible to maintain habitable conditions, explains Dr. Kalparapu. With different atmospheric composition or rotation characteristics, Venus could potentially support surface water even at its current orbital distance. The study of exoplanetary systems has revealed that planets with characteristics similar to Venus are common throughout the galaxy. These super-Earths and hot Earths provide natural laboratories for testing our understanding of planetary evolutionary pathways. Dr. Lisa Kaltenegger from Cornell University has studied the atmospheric evolution of Venus-like exoplanets using data from the Hubble Space Telescope and ground-based observatories. Her research suggests that the evolutionary pathway taken by Venus might be relatively common for planets in the inner regions of planetary systems. We're finding that many exoplanets show signs of atmospheric evolution similar to what Venus experienced, notes Dr. Kaltenegger. This suggests that Venus's evolutionary pathway, while extreme, might represent a common outcome for planets that form too close to their stars or experience major evolutionary disruptions. The search for alternative evolutionary pathways has also revealed potential future scenarios for Venus's continued evolution. The planet's atmospheric loss to space is ongoing, and computer models suggest that Venus could eventually lose much of its massive atmosphere over the next few billion years. Dr. Hunter Waite from the Southwest Research Institute has calculated that Venus's atmospheric escape rate could accelerate as the Sun becomes more luminous during its main sequence evolution. This could eventually lead to an evolutionary transition where Venus becomes more Mars-like, with a thin atmosphere and exposed surface. Venus's evolutionary story is not over, explains Dr. Waite. The planet could undergo additional major transitions over the next few billion years as its atmosphere continues to evolve and the Sun's luminosity increases. Understanding Venus's evolutionary pathway also provides crucial insights for assessing the potential habitability of Earth-like exoplanets. The factors that led to Venus's transformation: rotation anomalies, atmospheric composition, orbital distance, and magnetic field evolution, are all parameters that can be constrained for exoplanets. This knowledge is particularly relevant for the search for potentially habitable worlds around other stars. Planets that show evidence of rotation anomalies, atmospheric loss, or other signatures similar to Venus's evolution might be less likely to maintain long-term habitability. The study of evolutionary pathways reveals that Venus's backwards rotation is not just an astronomical curiosity, but a crucial marker of the planet's entire evolutionary history. This single characteristic connects to atmospheric evolution, magnetic field generation, geological activity, and habitability in ways that demonstrate the fundamental interconnectedness of planetary systems. As we contemplate the different paths Venus could have taken, we're reminded that planetary evolution is not deterministic, but rather represents one outcome among countless possibilities. The backward spinning world we observe today stands as a monument to the path not taken, a permanent reminder of how different our solar system could have been with just slight changes in the cosmic dice that determined each world's fate. Chapter 10: Comparative Worlds. To truly understand the significance of Venus's backwards rotation, we must examine it in the context of planetary rotation throughout the universe, comparing our sister planet's anomalous spin to the rotational properties of worlds both within our solar system and beyond. This comparative analysis reveals that Venus represents one of the most extreme examples of rotational evolution in the known universe, a cosmic outlier that challenges our understanding of how planets should behave. Within our own solar system, Venus's rotation stands in stark contrast to the orderly spinning of its planetary neighbors. Mercury, despite being tidally locked to the Sun in a 3-to-2 spin orbit resonance, rotates in the prograde direction with a period of 58.6 Earth days. Earth, of course, maintains its familiar 24-hour rotation that has remained relatively stable for billions of years, contributing to our planet's magnetic field generation and climatic stability. Mars presents an interesting intermediate case, with a rotation period of 24.6 hours that closely matches Earth's, but with an axial tilt that varies dramatically over millions of years due to the absence of a large stabilizing moon. This comparison highlights how Venus's backwards, ultra-slow rotation represents an extreme departure from the norm even among our planetary neighbors. Dr. Heidi Hamel from the Association of Universities for Research in Astronomy has studied rotational properties throughout the solar system using data from multiple space missions. Her comparative analysis reveals that Venus's rotation is uniquely anomalous, even among planets that have experienced major evolutionary disruptions. When we look at rotation rates and directions across the solar system, Venus stands out as the most extreme case, explains Dr. Hamel. Even Uranus, which rotates on its side due to a massive ancient collision, still rotates in the prograde direction. Venus is the only planet that spins backwards slowly. The gas giants provide additional context for understanding rotational evolution. Jupiter and Saturn rotate rapidly, with periods of about 10 and 11 hours respectively, preserving the high angular momentum they acquired during their formation from massive rotating disks. These planets demonstrate what normal planetary rotation looks like when unperturbed by major evolutionary disruptions. Uranus and Neptune, while rotating more slowly than Jupiter and Saturn, still maintain prograde rotation despite evidence for major collisions or evolutionary events in their past. Uranus's extreme axial tilt of 98 degrees suggests it was struck by a massive object, yet it retained prograde rotation, making Venus's complete reversal even more remarkable. The comparative analysis becomes even more striking when we examine the rotation of planetary satellites. Most large moons in the solar system are tidally locked to their parent planets, showing the same face at all times due to gravitational forces. This represents the expected endpoint of tidal evolution for closely orbiting bodies. However, even among tidally locked moons, retrograde rotation is extremely rare. Only a few small, distant moons of the giant planets show retrograde orbital motion, and these are thought to be captured asteroids or comets rather than objects that formed in place. No large moon anywhere in the solar system exhibits the combination of retrograde rotation and slow spin that characterizes Venus. Dr. William McKinnon from Washington University has studied satellite rotation throughout the solar system. His research emphasizes how unusual Venus's rotation is when compared to the tidal evolution of moons. Satellites provide natural experiments in tidal evolution, and we see a clear pattern towards synchronous rotation in the prograde direction. Venus's evolution towards slow retrograde rotation represents a completely different evolutionary pathway. The study of exoplanetary systems has revolutionized our understanding of planetary rotation by providing thousands of additional examples for comparison. The Kepler Space Telescope and ground-based transit surveys have revealed planets with a vast range of orbital and rotational characteristics. Yet Venus-like rotation remains extraordinarily rare. Most exoplanets discovered by transit methods orbit much closer to their stars than Venus does to the Sun, placing them in regimes where tidal forces should drive evolution towards synchronous rotation. These tidally locked exoplanets typically show one hemisphere permanently facing their star, representing the expected endpoint of tidal evolution for close-in planets. Dr. Rory Barnes from the University of Washington has modeled rotational evolution for thousands of exoplanets discovered by transit surveys. His research reveals that while synchronous rotation is common for close-in exoplanets, slow retrograde rotation like Venus's is virtually unknown. Among the thousands of exoplanets we've discovered, none show clear evidence for Venus-like rotation, notes Dr. Barnes. This suggests that either the conditions leading to such rotation are extremely rare, or Venus represents a transitional state that most planets don't maintain for long periods. The absence of Venus-like rotation among exoplanets could be explained by several factors. Most discovered exoplanets orbit much closer to their stars than Venus does to the Sun, placing them in tidal regimes where evolution towards synchronous rotation occurs rapidly. The specific combination of distance, atmospheric properties, and evolutionary history that led to Venus's current state might be extremely rare. However, observational selection effects also play a role. Current techniques for measuring exoplanet rotation are limited to specific types of planets and orbital configurations. Many Earth-like exoplanets at Venus-like distances from their stars remain undetected or poorly characterized, making it possible that Venus-like rotation exists but has not yet been observed. The James Webb Space Telescope and future missions designed to study Earth-like exoplanets will provide better opportunities to detect and characterize planetary rotation in other systems. These observations will help determine whether Venus's backwards rotation represents a rare cosmic accident or a more common evolutionary pathway. Comparative studies of planetary atmospheres provide additional context for understanding Venus's uniqueness. The planet's massive, slow-rotating atmosphere creates circulation patterns unlike anything observed elsewhere in the solar system or among characterized exoplanets. Dr. Adam Shulman from the University of Arizona has compared atmospheric dynamics across multiple worlds. His research reveals that Venus's atmospheric superrotation, combined with its slow retrograde surface rotation, creates a unique dynamical regime that doesn't exist elsewhere in the known universe. Venus's atmospheric circulation represents a completely unique solution to the fluid dynamics equations, explains Dr. Shulman. No other planet we've studied shows this combination of rapid atmospheric circulation and slow, backward surface rotation. This atmospheric uniqueness extends to the coupling between atmospheric and rotational evolution. While other planets show evidence for atmospheric effects on rotation, particularly for tidally locked exoplanets, Venus appears to be the only world where atmospheric dynamics play a dominant role in determining the planet's rotational state. The comparative analysis also reveals how Venus's rotation affects its other planetary properties. The planet's lack of a magnetic field, extreme surface conditions, and atmospheric composition all connect to its rotational characteristics in ways that don't occur for other planets. Earth's rotation, for example, drives core convection that generates our protective magnetic field, enables plate tectonics through Coriolis effects, and maintains climatic stability through rapid day-night cycling. Venus's slow, backwards rotation prevents all of these processes, creating a cascading series of differences that distinguish it from every other terrestrial planet. Dr. Doris Breuer from the German Aerospace Center has studied how rotation affects planetary magnetic field generation across multiple worlds. Her comparative analysis shows that Venus's rotation rate falls well below the threshold needed to maintain core convection, explaining its magnetic field absence. Venus represents the extreme case where rotation becomes too slow to drive the internal processes that typically characterize active planets, notes Dr. Breuer. It's essentially a magnetically dead world due to its rotational properties. The comparison with Earth is particularly striking because of the planet's similar sizes and compositions. Both worlds formed from similar materials at similar distances from the Sun, yet their evolutionary paths diverge so dramatically that they now represent opposite extremes of planetary evolution. This Earth-Venus comparison provides crucial insights for astrobiology and the search for habitable worlds. The factors that led to Venus's backwards rotation, weather collision, tidal evolution, or atmospheric effects, represent potential hazards that could transform any Earth-like world into a hostile environment. As we survey the cosmic landscape of planetary rotation, Venus emerges as a unique and fascinating outlier, a world whose backward spin tells a story of evolutionary divergence unlike anything else in the known universe. Its rotation serves as a cosmic warning about the fragility of planetary habitability and the complex factors that determine whether a world becomes a haven for life or a hostile wilderness spinning backwards in the cosmic dark.